Hey everyone, I'm Hamd, and today we'll be discussing the basics of machine learning and its two main types, regression and classification. But first, let's quickly cover the AI hierarchy model. The overarching term for anything regarding simulation of human intelligence is artificial intelligence. This term is quite broad and could refer to decision making, reasoning, or generation. Next, we have machine learning, which is a branch of AI. Machine learning models take in data and learn patterns from that data to be able to make predictions without having to be explicitly programmed. And then we have deep learning, which is a type of machine learning that uses neural networks with many layers to learn complex patterns in large amounts of data. You probably noticed that this sounds a lot like how the brain works, and that's true. Deep learning algorithms were inspired by how the human brain works. And finally, at the bottom of the hierarchy, we have generative AI. It does exactly what it sounds like. It uses its training data to make new content. For example, we have ChatGPT for text generation, DALL-E for images, and Suno for music. Now that we've covered the hierarchy, let's return to our main focus, machine learning, which finds patterns in data to be able to make inferences or predictions. As an example, let's say we took a survey and collected the height and weights of 100 people. Plotted on a graph, it would look like this. A little messy. So to make predictions, we need to find a line that fits the general pattern, a sort of best guess that shows how height and weight are related. We could just connect all the points, but that would look like this. This is definitely not the way to go, because it overfits the data, meaning it follows every little fluctuation or outlier perfectly, but fails to capture the overall trend. It would make poor predictions on new or unseen data, which defeats the point of using machine learning in the first place. Instead, we want a smooth line that captures the overall relationship between height and weight, not just memorizing the data, but learning from it. So we could do what's known as a line of best fit, a line that shows the general direction of how the points change. That would look like this. This is obviously much better than connecting every single point together, but it's still not perfect. It assumes the relationship between height and weight is perfectly proportional, meaning if height were to change by a set amount, the weight would also change by that much, even when the actual relationship might be much more complex. Therefore, the best way to represent this data is a curve of best fit. This is much better because it allows for more flexibility in capturing the relationship between the variables, which might not follow a straight line. A curve can more accurately reflect how the points change, especially when the data can change at a faster or slower rate at different points, rather than a steady increase or decrease. So how do we make predictions using this curve? As an example, let's say we wanted to predict how tall someone would be if they weighed 65 kilograms. First, we would find 65 kg on the weight axis. Then we would draw a line out until we hit the curve. Finally, we go down until we hit the height axis, where we can take the reading. And that's our prediction, 175.5 centimeters. In a nutshell, that's actually how the first type of machine learning works, regression. Generally, you take two features, which in our example were height and weight. The regression algorithm will then find a line or curve of best fit that represents the general trend of the data. If we go back to our example of height and weight, the regression algorithm will plot the point on the graph and then create a line or a curve of best fit to represent as much of the data as possible while still allowing for generalization. Regression types are usually named after the shape of the curve they fit. There are many types of regression algorithm, but usually only four are used. First, we have linear regression. This is used when the data changes at a fixed rate. On a graph, it looks like a straight line and has the equation y equals mx plus c. Next, we have polynomial regression. You could consider it as if it is the opposite of linear regression. It's curved and represents data that changes at a varied rate. There are actually two polynomial curves on the image here, a quadratic curve and a cubic curve. And the equation follows the general form of a polynomial expression. Then we have logarithmic regression. This is used when the data initially changes very quickly, but then levels off and becomes flatter. This equation follows the form y equals a plus b times the logarithm of x. And finally, we have exponential regression, which again is essentially the opposite of logarithmic regression. it represents change that starts off slower and flatter, and then gains speed and shoots off. This equation follows the form y equals a times e, which is Euler's number, to the power of bx. Taking a look at a real-life use of regression algorithms, here we have some data of how the stock value of a company changed over time. Let's say you were thinking about investing, and you wanted to see a prediction of how the stock value would continue to change in the future. For this, you would want to use a regression algorithm, which may choose to do a logarithmic curve, a little bit like this. Then the regression algorithm would simply continue the curve in a process called extrapolation. Finally, the algorithm would generate varied points around the curve, similar to the other points. And that's your prediction. Now let's take a look at a new dataset. It uses height and weight again, but has a new column for animals. Plotted on a graph, it looks like this. We have height and weight on the axes again, but the points are different colors to represent the different animals. Let's say that we knew the height and weight of an animal, but we didn't know what animal it actually was. We would be able to plot it on the graph. And based on its position on the graph, you might be able to tell what animal it is. A hippo. And that's because it's clustered in with all the other data points for the hippos. If you were to create imaginary regions on the graph to represent where the points for each animal are, you would find that the new animal also falls in the region for the hippo. And that's the main idea behind classification algorithms. Just like regression algorithms, they can have multiple features, but unlike regression algorithms, they have one label, which in this case was the animal. The label is the thing the algorithm is trying to predict, and its presence also means you'll potentially have to go through your data and manually add labels to each data point. As a summary, classification algorithms identify ranges in which the corresponding category is the most common, to be able to predict the category if the values for the attributes are new. Back to our example, the classification algorithm would highlight the region where the category is most common, so that when a new unseen data point is given, it is able to identify the category. A real-life use for classification algorithms could be to predict a film's rating out of 5 based on its budget and box office revenue. Here our features are the budget and the revenue made, and our label is the rating. Let's say our data is here, a budget close to 1.5 million and revenue close to 2.5 million. To predict the rating it should get, we will apply the data to a classification algorithm, and it may generate regions that look like this. And based on the regions, the film is expected to receive a 4 out of 5. To summarize, machine learning finds patterns in training data to be able to make predictions and inferences based on it. Regression algorithms find trends in numerical training data to be able to make predictions based off of it. And finally, classification algorithms predict discrete classes by finding patterns among common data points. So that's it for the video. If you enjoyed or felt like you learned something new, please drop a comment or like the video. And if you want to see more content like this, feel free to subscribe and hit the notification bell. If you'd like to see the Python code that made the graphs or the slides, click the link in the description. Thanks for watching.